Make them pay for it. Yeah, there better be some reciprocity. I don't know, like something like they get information about math, but you get information about science. Like they better be giving you something in return for this. You know, I'm kind of kidding about that. All right. Anyway, so you did the do now problem. You foiled it out. Foiled it out. We don't even say that anymore. It's archaic. It's not really archaic. I love it. All right. Actually, you know what? I'm gonna bring it back. Have you ever heard the term foil?
I've heard foil, but no. Actually, I think I've heard foil it out.
Cartoon villains. Wow.
Right, exactly, yeah, in some other context than math. All right, so this is actually how I learned to double distribute. It's just an organizational strategy. It doesn't really give you any more insight or knowledge than the other approaches that we use. But the F stands for first. The O is outer. The I is inner. And the L is last. All right. So what are we referring to? When you have a product of binomials, you have the first terms. All right. You multiply the first terms. Yeah, I know we did it already. That's why it's a do now. Quality control, wonderful. So the first values multiplied gives you an x squared. Take your outer values and multiply them. You get a negative 2x. Take your inner values and multiply them. You get a 2x. And then your last values, multiply them. And you get a negative 4. It's exactly the same progression in the double distribution process. You know, if I multiply the first values and then the outer values, it's taking the x, distributing it to each term of the second binomial. And then the inner values and the last values, taking the 2 and distributing it to each term in the second binomial. I only bring this up because when I was looking at your last test, that was the most common error, just losing track of the multipliers when you're distributing things out. So you go through the problem, you have every intention of multiplying each relevant piece together, but you lose track of things along the way. All right, so how do you avoid that? Well, you come up with alternative strategies to help you do it, right? So what happens here? The negative 2x and the 2x, what happens? They cancel each other out to what? To 0, all right? Because there's two types of cancellations. There's a cancellation to 0, and there's a cancellation to 1. Cancellation to 0 happens through addition or subtraction. Cancellation to 1 happens through multiplication or division, all right? That's going to become more and more important as we go along, all right? But in either, way that you think about things, this becomes x squared minus 4. All right. So distribute 2x times 2x. Well, I was going to write 2x as a quantity squared, but I'll just write it as 4x squared. Take the outers, multiply them. Take my inners, multiply them. And then my last values, also multiplying. All right, so 4x squared minus 1. All right, because again, those two middle terms are going to cancel out. Now, if you do a little compare and contrast between numbers 1 and 2, I know one's a little messy now, but they're the same two expressions, just one with a plus and one with a minus. Same two expressions, one with a minus, one with a plus. All right, so the question might be, if something is in that same form, will it always work out this way where those two middle terms cancel out? All right, the answer is yes. All right, so those are what are known as conjugates. If two expressions are what are known as conjugates, their outer and inner terms will cancel out. Questions? Yeah. All right, So we'll kind of formally discuss this here. The difference of two perfect squares. I don't like throwing the word perfect in there because I like, I'm going to go with red here, difference of two squares, because then you have a nice little acronym. Dots. It's the dots situation.
I'm really sorry.
All right, so difference of two squares. That's how, they call it difference of two perfect squares, but then the acronym is going to look stupid. So, dots. Yeah, I don't know. So, difference of two squares. All right, a square number is referenced as a perfect square. And also, to be honest with you, this technique, yeah, it's ideal for perfect squares, but it'll work for anything that's a squared value. So it doesn't necessarily have to be a perfect square. We can get radicals involved here, and we'll see that in a little bit. All right, so what does this look like? Well, you have something in the form of a squared, well, I'll write in the form of a squared minus b squared. All right, so anything that has that form. All right, the reason why that form is relevant is because you have a difference you have two things that are each squares. All right. So that's where the name comes from. And that's important because if something is not a difference of two squares, you're not going to use this technique. You'll use some other technique if it's factorable at all. All right. So knowing the name of it dictates how it's structured. How it's structured will dictate how you go about factoring it. All right. So like in this case, more than probably a lot of other topics, the vocabulary is really important, all right? And we'll talk about other types of relationships like sum of two squares, what happens there. Maybe we'll get involved with some cubes down the line, we'll see. But the idea is if you know what it's called, you say it correctly, and you'll think about it correctly, and then when push comes to shove, you'll write it all correctly. That's the idea anyway. All right, so we have the examples above that kind of led us to a structure related to this. So we're kind of discovering it, but not really, because if you follow the format here, you see that we have two binomials that are being multiplied, and it gives us something in the form of difference of two squares. All right, so we can assume that we're going to have two binomials multiplied. Let me just bring it in a little bit. The middle terms, the outer and inner terms, are going to cancel out. So what that's telling me is that I have to have two expressions that are identical except for the sign in the middle. The sign in the middle has to be alternating, one positive, one negative. Doesn't matter which is which. All right. So what I want to be thinking about is how can I get to a product of x squared? X times x. I also need to get to a product of 16. I'm going to do that how? The 4 and 4 will get me a 16. If one of them's negative and the other's positive, when we distribute this out, or use the FOIL process if you like that, it's hit or miss, you should see that whatever this expands out to will simplify to equal the x squared minus 16. That's the idea. You can check by foiling, you can check by double distributing, but when all is said and done, you should get back to this. All right. So, number 2. Same idea. It's got the right form, so one is going to be negative, the other is going to be positive. I need two identical numbers when multiplied that'll give us 9x squared. 3x, yep, 3x times 3x.
5 and then positive 5.
5 and 5. 1 negative, 1 positive. All right, this one is where it starts to get a little funky because sometimes it's a multi-step problem. We'll take a look. And also we have a power of 8 here, which is definitely more interesting. All right, so the question would be, again, is it in the appropriate form? Is it a difference? Yes. Are there two things? Yes. Are they both perfect squares? Or are they both squares?
Yes.
Yes. 36 is a perfect square. Anything to an even power, any variable to an even power is a perfect square. All right, variable raised to an even power is considered perfect. All right, so it's got the right form, the right structure. So 36, 6 times 6, minus plus, two identical values that multiply to d to the 8th, d to the 4th. All right, so you do a little guess and check and say, okay, well, I think it's d to the 4th. Keep the base at the exponent. 4 plus 4 is 8. But what's a shorter way to do that? How do they get really from the 8 to the 4 without guessing? What operation would allow you to get from the number 8, forget about the fact that it's a power, from the number 8 to the number 4?
Division.
Division of 2. Right? So it looks like if we divide our power by 2, we get the appropriate expression. Did that happen here?
No.
2 divided by 2 is?
1.
1. Okay, that took a little longer than it probably should have. What's the understood power here?
1.
1. All right, so that checks out. All right. So this part, when you look at the expanded form, the 6 plus d to the 4th, not the right form. It needs to be a difference of 2 squares. All right. Now, so that's out. We don't have to worry about that. But this one, you can look at it. Even though 6 is not a perfect square, it doesn't actually have to be a perfect square, because what I was saying here is that the term difference of 2 perfect squares is kind of a misnomer. This technique can be used even if you're not dealing with perfect squares, as long as there's a difference between 2 things. So it's the difference of 2 squares technique. Most often and most usefully, it applies to perfect squares, but we could use it in other cases. So let's take a look. Oh, back to the pen. So I'm going to take that highlighted part and expand that out. I'm going to leave the 6 plus d to the 4th alone. All right. So this one, I'm going to treat it as if each part is a perfect square, even though that's not the case. All right. I have a difference of 2 things, and that's really all I need. All right. So if I'm following the same structure, I'd have a minus sign and a plus sign. And these 2 pieces are the parts that I would have to worry about. I'd have to consider those components. The d to the 4th would become what?
D to the 2nd.
D to the 2nd. All right. The big question would be, okay, now what do I do with the 6? All right. So I need 2 identical numbers that would multiply to equal 6. Well, you could try it in your calculator, you know, guessing and checking. You'd say, all right, let me try 2 times, well, that's 4. 3 times 3 is 9. If I'm going to get to a 6, it's got to be something between 2 and 3, right? So probably a decimal. So if that's the assumption, then maybe the calculator is not the way to go. All right, so let's just go back for a second to the previous example. How did I get from the 25 to the 5? Divided by 5. But how did we know it was going to be a 5 to begin with? For the variables, it's easy enough. We could divide the power by 2. But for the numbers, it's a little bit of a different story. Give me an operation that's not division or subtraction. Give me an operation that would take 25 and make it into a 5. Or maybe a 9 and make it a 3. Square root. All right? So does that idea seem to apply? Is this the square root of that? Yeah. This is the square root of that. So could we then say that if I were to take the square root of this first term in my binomial, that would give me the first term in the expansion? The square root of the second term would give me the second term in the expansion? Seems reasonable. All right, check that back with this one. Did that happen here? Square root of x squared is x, right? Square root of 16 is 4. All right. So the question would be, what is the square root of 6? And the answer, the short answer, is some funky decimal, right? Because it's irrational. So why not just write it as the square root of 6? All right, because if that's what we're doing, we're taking the square roots. Square root of square root of this would become this and this. The square root of 6, it's either some funky decimal that you would round, or you would just write it as the radical 6. All right. So this is a nice little extension. It's not technically a requirement, which is good, because from your perspective, it's like, well, I don't have to worry about it. This would be a final answer because we're going to stay away from radicals for the most part in this course related to this topic. But anytime you have a situation related to a problem like this, on a quiz, on a test, any exit ticket that I give you, if you go the next step, there will be some bonus credit in it for you. All right, because anytime you do something that's above and beyond and meaningful, I like to make it worth your while. All right, so if this makes sense to you, this concept, and in fact, the radical 6 minus d squared could even go further with more radicals. It would get a little kooky. So we could stop here, but we could expand it into the world of radicals, and that'll kind of set you up moving forward, right? So if you can handle something like that, there will be a little bit of bonus credit in it for you. So anytime we have a problem like this, I'll tell you where you could stop, and then what it would look like if you were to continue on. All right? Hopefully that makes some sense. All right, so general rule for a difference of perfect squares, or difference of two squares, as I like to say it. It seems that we're taking the square root of the first term. So what's the square root of a squared? And the square root of my second term, so b. All right. So a nice little general rule there. So provided you can either follow this progression more so in like numbers 1 and 2, or you can identify the A and B values, you'll be able to handle any question I can throw at you. Some of them require some additional steps like GCFs and things like that, but nothing too crazy. So here, let's take a look at number 4. We could just go right the way we were doing it with 1 and 2, but I want to actually use the rule here. So I'm going to match this with the general form, which is a squared minus b squared. All right, so if that's the case, there's not much we could do. I mean, there's really nothing we could do with the t squared. T squared is just t squared. But what I want to do here is I want to write 81 as a power of 2. All right. So what number squared is equivalent to 81? 9. So now I know my A value and my B value. All right. So if we know that a squared minus b squared expands out to a minus b, a plus b, the a value is t, the b value would be 9 with a minus and plus.
Wait, which answer do you want? Do you want both?
That is the answer.
Okay. Yeah, that's
All right. The notation is going to become more and more important as we go along.
Wait, so we have to show it that way?
Be prepared to, yeah. Yeah, because I could ask you to say, determine the factors, but also indicate what the a and b values are. All right. The factored, thinking multiple choice question. Which of the following a and b values would make up the factored form of, and we would go from there. So there's all the different ways that it could be asked. And this concept, it's fairly simple in terms of getting an answer. You can get the t squared from t squared minus 81 to the final answer very quickly without doing really any of this stuff. But when we expand it to more complicated things down the line, you're gonna have trouble if you're avoiding the notation. Can't avoid the notation forever. There will be a price, and you'll have to pay it at some point if you do that. All right. So we're writing each part as a power of 2. 4x squared would become what? 2x. All right, 9 would become what? 3. All right, so we have our a plus c and our b. All right, so we know it's in the form of a minus b, a plus b. So 2x minus 3, 2x plus 3. These little things. You'll experience it, and it's again unfortunate that you got to wait through geometry in order to get to algebra 2, but it's these little things that will make the difference between success and the opposite of that in algebra 2.
If the exponent was like 10, would it have to be like a perfect square in order for you to like distribute it without the radical thing?
It doesn't have to be a perfect square. In that case, it would be, because the power of 10 is still perfect, because any even power is considered perfect. It's when you have odd powers that things are going to get crazy.
Would you write like a defense or something?
Yeah. Do we have an example like that? Let me create one. Further down the line. It's going to create a new video if I flip pages. So let me just make it like a B, like a 5B question. So let's say we have
a 1 minus 10b.
Well, I don't want to use one that's already there. I'm just going to create a new one. So let's say we have 4x to the 10th minus z squared y to the 12th. That's a good one. All right, so each part we want to write as a power of 2. The number should be easy enough. So if I want to get to a 4 by raising it to the second power, the number raised to the second power must have been a 2. All right, x to the 5th. Oh, that's a poor quality 5. Let me fix that. All right. Now, in terms of the other part, the z squared y to the 12th, a little bit of a different story. Still the same technique, though. Divide each of your powers by 2. So z y to the 6th, exactly. All right? Because really what we're doing here is taking the square root and then writing it as a power of 2, because a square root and a power of 2 will cancel each other. So you're left with something equivalent to what you started with. All right? So then my expansion here with the appropriate a and b values would be 2x to the 5th minus zy to the 6th, and then also 2x to the 5th plus zy to the 6th. All right, good question.